Hello everyone, welcome back to part 2 of chapter 14. In chapter 14 we're going to look at the methods of initial rates, and this is how we're going to actually plug numbers in and solve for those exponents x, y, and z in the rate law expressions. So I have some general rules for this. You're going to write the general rate law expression. You're going to determine the numerical values of x, y, and z. You're going to determine the numerical value and the units of the specific rate constant k. Then you're going to use a line of data. Remember, we have to use experimental data to do this. We're going to use one line and plug those values in and see if we can solve for the actual value of k. And then we're going to write the final form of the rate law expression for the reaction using the numerical value of k and its exponents. So we're given a general rate law expression such as this, okay, and so this was a plus b gives us whatever. And we're going to solve for x. So if we solve for x, we're going to need some experimental data where b stays the same. And if b stays the same and there's no change in concentration, then the concentration of A changing is what's going to affect the rate. And so that's going to allow us to calculate what X was. If we want to solve for Y, then we need one where A is constant, where only B would affect the rate. So if you don't ever have a time where one of them was the same, then you're going to have to use an exponent method, and I'll show you that at the end of this lesson. So our first example here is that the following rate data were obtained at 25 degrees C, because remember we have to stay at one temperature or that's going to affect the rate law constant and change it. That's the only thing that changes the rate law constant. Alright, and so it's just 2 moles of A plus B gives us 3 moles of C. And so we have 3 separate experiments that we ran in the laboratory where we had a 0.1 molar concentration of A and a 0.1 molar concentration of B, and the rate was 2 times 10 to the minus 4. In the second experiment, I increased A to 0.2, I increased B to 0.3, and my rate doubled. And in the third experiment, my molarity of A was again back to 0.1, my molarity of B is 0.2, and my rate is 2 times 10 to the minus 4. So these are 3 separate experiments, and I need this data in order to figure out which one of these concentration changes is changing the rate of formation of C. So I've just recopied it here so I'll have a little room to write this and show you kind of how we look at it. So if I want to find B, and you can do either one, it doesn't matter. But if I'm going to find B, I'm doing that because I see that there are 2 experiments where the initial concentration of A is the same. Okay, so I'm going to compare experiments 1 and 3 because A is constant and B changes. Okay, so that's why I'm doing this. All right. So in my rate law is rate equals K times A to the X times B to the Y, because that's the general form of it that it always is. And so when I look at this, A stays the same. B, the concentration of B goes up times 2, right? It went, because I'm looking at these 2, so it went from a 0.1 to a 0.2, so that's times 2 change for B in experiments 1 and 3. So the way I figure this is that it increased by 2, so 2 to the y equals what? The rate stayed the same, okay? It stayed the same, so the rate was times 1. So the rate went up only times 1 because it stayed the same. So 2 to the y equals 1. And I know, if you recall, I was telling you y to the 0 is equal to 1, y to the 1 equals y, etc. So 2 to the y equals 1, so y must equal 0, because 2 to the 0 equals 1. With me? And I'm doing that because I know what these are, so I don't have to do a lot of math to figure that out. Therefore, B is a 0 order. Now I need one. Now I know that B is a 0 order, so I know that it doesn't change anything. So I don't have to worry about it staying the same, because it's not going to have any effect on the rate, because I doubled it and the rate stayed the same. So I don't have to have one where it's the same. So if I'm looking at A, I'm going to compare. I need to get one where maybe the rate changes. And in this case, 1 and 2, I go from point 1 to point 2 of A, and I went from 2 times 10 to the minus 4 to 4 times 10 to the minus 4. So I'm going to compare 1 and 2, okay, and see what happens with A. So A increases times 2, and the rate also increases times 2. So 2 to the x equals 2. X equals 1, because 2 to the first power equals 2. So 2 to the x is 2 to the first, so x is 1. Therefore, A is first order. So I'm going to rewrite this as the rate equals K times A to the first times B to the 0. And I really don't have to write that B to the 0 because that's times 1. So it's really K times A, because A to the first power is A. With me? Again, there is a section on this in mastering in the math tutorial, so if you need to go back and review this stuff, go back and review it. Alright, so we are 0th with respect to B, and first in A. So the total order is 1 plus 0 equals 1. So the total order is also first overall. Now the second part of this, it wanted me to figure out what K was. So I go back to my original. I now know what those are. So the rate equals K times A. So if I rearrange this, K equals the rate divided by the concentration of A. And so I can just pick any of them I want to. I'm going to pick the first one because it's the first one I come to, but you could do any of them. Alright, and so the rate of the first experiment, so I'm going to use experiment 1. 2 times 10 to the minus 4, and that's molar per second, divided by the concentration of A in that same experiment is 0.1 molar. So K is equal to 2 times 10 to the minus third second minus 1, because those molarities canceled. And remember, 1 over second is the same as S minus 1. That's where that's coming from. And so the rate equals 2 times 10 to the minus 3 times A. So what that's given us is that at any concentration of A now, no matter what I do to the concentration of A, I can tell you what the effect on the rate is, because that is the specific rate expression of this reaction as long as it stays at the original 25 degrees C. If I change the temperature, it will change the K. Okay? So that's how you do that. The following data were obtained for following reaction at 25 degrees C again. What are the rate law expressions and the specific rate constant for this reaction? Now this time we have 4 different things, okay? So what I'm looking for is if I can figure out one that doesn't have an effect, then I can go ahead and get rid of that one. So what I'm going to do is I'm going to look at the rates, and I'm going to look and see if I can find an experiment where the rate stayed the same. And so here's, in 1 and 3, the rate stayed the same. All right, so in this one, A, the molarity of A stayed the same, the molarity of B stayed the same, but the molarity of C tripled. I tripled this, so this was times 3, but my rate didn't ever change. So without even doing any math, I know if I tripled this concentration, everything else stayed the same, it had no effect on that reaction, so I know that that's a 0. Okay, so it's 0th because it has no effect on it. And so I don't have to worry about C because it has no effect. So now all I have to worry about, and a lot of times if you have 3, one of them is not going to have an effect. So if you can figure that out, and again, I looked at 2 reactions where the rate stayed the same, and I looked, this stays the same, B stays the same, C changed, but no change to the rate. It stayed at 2 times 10 to the minus 4. Okay? So I don't have to worry about that. So I already know for my rate, because in this one I have 3, right? So the rate, the general expression for this is K times A to the X times B to the Y times C to the Z. Okay? And I've already figured out that C has no effect on the rate, so I know that's a 0, so I know I'm not going to have to write that in the rate expression. So now I just have to worry about A and B. So I'm going to look at those, and you can do them either way. I usually try to do whatever's easiest, but you know me. So for C, I'm going to compare 1 and 3. Why am I doing that? Okay, I got 1 and 3. Okay, because, oh, sorry, that's how I found the C, right? So it was a 0, and I eyeballed that on the first slide because I know that I raised the concentration 3 times for C, and it had no effect on the rate. Okay, and so I know that that is a 0 order because it's not doing anything. All right, so now I'm going to look at B. As I said, just do these. So for B, I'm going to compare 1 and 2. So 1 and 2. So because A is the same and B changes, okay? So for B is going to go up, so A is constant, right? And so B goes up times 3. And what happens to the rate? It goes up times 3. The rate goes up times 3. So I'm going to say then that 3 to the Y equals 3. So 3 to the y equals 3. And we already said y to the 0 equals 1, y to the 1 equals y. So 3 to the first is 3. So y equals 1. So B is first order. So now I'm going to go back and look at A. And remember, I've got to have one where B is constant this time. And so I can't use 1 and 3 because they're both constant. So I'm going to have to compare 2 and 4. All right, so 2 and 4 to figure out A. So 0.2 to 0.6 is times 3 increase. So A goes up times 3. What happened to the rate? You got to watch this right here, okay? Because it's 6 times 10 to the minus 4, and it's 1.8 times 10 to the minus 3. So that's the same as doing 6 and 18, okay, if you're looking at magnitude of numbers. So you can put those in and divide them and see. But if you divide this one by this one, or 18 by 6, you're going to also get what? 3. So 3 to the x is equal to 3. Okay, oops, 3. So x is also 1, and that's also first order for A. So our actual rate expression is rate equals K times A to the first times B to the first, but that's really A times B, right, the concentrations. And so if I want to find out what K is, I rearrange that, and K is equal to the rate divided by the concentration of A times the concentration of B. And so K, and again, you can use whichever one you want. I almost always pick the first one just because it's the first one I come to, I guess. But the rate is 2 times 10 to the minus 4. This is for experiment 1. And the A concentration is 0.2, and the B concentration is 0.1. And so when I put that in my calculator, make sure your calculator is your friend. 1 times 10 to the minus 2, molar minus 1, second minus 1, because that's molar per second, right? And that's molar, molar. So you end up with 1 molar left on the bottom. So that's molar minus 1, second minus 1, okay? And so the actual rate would be 1 times 10 to the minus 2, m minus 1, s minus 1, times A times B. And that's the specific rate expression. Now let's go back for just a second because I didn't do something. What's the overall order of this? So the overall order, remember, is the sum of the two orders. So I had a first order and a first order, so 1 plus 1. And if you count C, it was a 0. Okay, so the overall order is second order. So it's first order in B, first order in A, and second order overall. And here is our specific rate expression. The good thing about these pre-recorded gizmos is you can actually go back and redo this and watch me again and go through it if you've missed something. And then if you have questions, you can send me questions. But typically, you look at these and then you try. I'm going to have you do some practice problems with them and see if you can figure them out. Because, if you'll try to work them first, a lot of times you can figure it out. Okay, so here's a third kind. This is one where I have stuff missing in the chart, and this is where you got to know how to rearrange equations. So consider a chemical reaction between compounds A and B, and I'm already telling you basically what the rate expression is, because I'm telling you that it's first order with respect to A, first order with respect to B, and second overall. Okay, so what I'm telling you is this is first order, this is first order, and so there's only two things that are going to be contributing, and so 1 plus 1 is 2, so it's second overall. So that's another way of me saying that the rate is equal to K times A to the first power times B to the first power, but we know we don't have to write it like that. It's K times A times B. Right? Right. Okay. So here's that same data. So this time I got stuff missing. Okay, so it's telling me the rate law. So I've got this general rate law already. So the rate equals K times A times B. I already knew that X and Y are 1, both of them. So it already told me that because it said this is what the orders are. If it didn't tell me, I could have figured it out probably, right? So because it has things missing though, I kind of have to have that information. All right, so I know it wants me to figure out, let's see. It wants me to figure out the concentration of A in experiment 2 and the concentration of B in experiment 3. Now, one thing I've got to know, if I'm going to be able to work this, is I've got to know what K is. And I have information where I can figure out K, because K is going to equal the rate divided by the concentration of A times B. So I have to look up here, and as long as I have one experiment that has all those three things in it, I can figure out what K is. And if I know what the rate constant is, then I can just solve for whatever the unknown is. Okay, so stay with me. So I'm going to use the complete experiment, which in this case is going to be experiment 1, because it has all three of those things. It has a rate, which is 4 times 10 to the minus 3. It has a concentration for A, which is 0.2 molar. Sorry, I should write these for you. And then 0.05 molar for B. And so I can plug that in. Okay, and when I do that, I'm going to get 0.40 molar minus 1, second minus 1, because I've got a 1 molar there, 1 molar there, 1 molar there, so I have 1 left over. And then I have the second, which is per second, so it's down here, right? Okay, so now that I have the rate, then all I have to do is plug this in, and with the other information I have, if I have 2 of the 3 in an experiment, I can solve for the other one as long as I know the rate. So if I want to find what A is, I'm going to rearrange this, okay, so that A is equal to the rate divided by K times B. Now, if you have trouble rearranging equations, and I kind of drilled y'all on this a little bit if you had me for 111, but there is something on the mastering that kind of goes through this and how you do this, okay? So again, this is a math thing that you might have to review. 1.6 times 10 to the minus 2. All right, so I'm solving for A, so I'm using experiment 2, because that's where A is the unknown. So so I'm using the rate from experiment 2, which is 1.6 times 10 to the minus 2 meters per second. And I'm going to use the rate, which I found out was 0.40 meter minus 1, second minus 1. And then I'm going to multiply that by 0.05 molar, which was the concentration of B. And when I put that into my calculator, now you need to make sure you know how to use your calculator too. So these examples are an opportunity for you to work them and make sure when you put them in your calculator that you get the same thing I do, okay? Because it's all about parentheses when you're dividing by numbers, so don't forget to do that. All right, and then I come up with a pretty simple number, 0.8 molar. So that's the concentration of A in experiment 2. All right, so in the experiment 3, it wants me to know what the concentration of B is. And so it's the same exact equation, except I just put A in there, okay? So once I found K, this is pretty simple. You just plug and play, right? So your rate is equal to K over the concentration, or rate divided by the concentration of A times K will give us the concentration of B. So 3.2 times 10 to the minus 2 molar per second divided by our old buddy K, which is 0.40, because remember, as long as I don't change the temperature, that's going to stay the same. And then times the concentration of B in this experiment, which was 0.4 molar. All right, and so when I do all that math, I'm going to come up with 0.20 molar for the concentration of B. So this concentration was 0.8 and this concentration was 0.20. On these where you have to do this, you've got to be able to figure out what K is by plugging it into the one where you have all the information, and that was experiment 1 in this case. So those are really the 3 types of problems that you're going to see based on these initial rates. The other way to do this is to solve for exponents. Okay. Now, I've had some students say they just as soon do it this way every time, which I kind of think is funny. But you know, not for me. But I'm going to do it. Let's see. I think I do it somewhere. Yeah, when we get to example 14.2, I'm actually going to work a problem like this. Okay, but basically, this is just telling me what the experiment was. All right, so instead of writing it like this, I just have it tabular. So you have 6.75 rate. You have 3 for the concentration of A in the first, and then you have 2 for the concentration of A in the second one. So this is 2 experiments. All right, and so the rate in experiment 2 was 3. So if you're trying to figure out what the exponent is for A, you look at the 2 experiments, you look at the rate, and you look at the concentration, and then you're going to write in the ratio and proportion basically. So you would do the rate of 1 over 2, so that's the 6.75 and the 3.0, okay? And then set that equal to, it's got to be in the same experiment, so 3 over 2, and that whole thing will be raised to the x. Now, if you're raising something to a power, the way to get rid of it is to take the log of it, okay? So in this next step, what we've done is we divide 6.75 by 3 and you get 2.25. Okay? And 3 divided by 2 is 1.5 raised to the x. So that was that second part. And so the way you solve for x is you have to take the log of both. So you would have x would equal the log of 2.25 divided by the log of 1.5. Okay, because you're doing 2.25 divided by 1.5, right? And you have to take the logs of the numbers to get your coefficient down, your exponent down. It's a math rule, I'm not making it up. Okay, and so when you take the log of, so that becomes the log of 0.352 divided by 0.176. Okay, so that's the log of this number, the log of that number, and x comes out all over 2. Okay, it's really, really close to 2. Okay, so so this is going to be what your x value is, and so your a would be raised to the second power. So see why I like to see if it's one that we know, like it's a 0 or a 1 or a 2. If they come out even, you don't have to do all of this extra math. I'm actually later going to work one both ways for you and kind of remind you of how this is done. That's why I just kind of did it on here. Okay, maybe I'm doing it now. Nope, these are, yeah, I am. Okay, all right. So 14.2. So 14.2, we've got, and again, I can eyeball this one, okay? And when I say eyeball, I look at it and see if one goes up times 2 and one goes up times 4, then it's one increases to the second, one increases to the fourth, so 2 to the x equals 4, that kind of deal. That's why I'm doing it this way. So I'm going to go back and I'm actually going to work this one. If you can keep this in your head, I'm going to go back one and I'm going to use that data that I just showed you. So you should have a copy of it if you got your in class, okay? So because I don't want to take the time to rewrite it because it'll take too much time. But our overall rate expression, just like it always is rate is going to be equal to K, and we had NO2 to the x times CO to the y, okay? And then I have some rates. Now, A and B, right? So really we just, like x is going to be the exponent for the first one, so I'm not using that for this, okay? I'm using the data table that's in example 14.2. So for NO2, so I'm doing this the old way. We've already done it like 3 times. You're going to use 1 and 2, all right, because CO is constant. So I'm looking for NO2. So NO2 goes up times 2. And when I do that, the rate goes from 0.0021 to 0.0082. That's times 4. All right, the rate, so the NO2, so since it's not on here, I'm going to write it 0.1 to 0.2, okay, because we're using 1 and 2. And then the rate went from 0.0021 to 0.0082. So that's times 4. 0.0021 times 4 is 0.0082. And you can divide those if you need to figure out what the number is. All right. So remember how I do this. So that means that 2 to the x equals the rate change, which is 4. Now 2 to what power is 4? 2 to the 0 is 1, 2 to the 1 is 2, 2 squared is 4, okay? So x is 2 because I squared it. So it's second order for NO2. For CO2, I'm going to use 2 and 3 because in 2 and 3, NO2 stays the same. And CO goes from, NO2. NO2 stays the same, yep. So CO2 goes from 0.1 to 0.2, so it goes up times 2, and the rate for 2 to 3, it was 0.0082, and it goes to 0.0083. And ladies and gentlemen, that's basically the same number, all right? So it went up times 1, because that's a lot of decimal places, right? So there's not enough difference in that to really matter. So that went up times 1. So the way I do it is 2, and this time's CO2, so it's to the y, right? So 2 to the y equals 1. So y must equal what? 1. Yes. Yay. Because anything raised to the first power is 1. So 2 raised to the first power is 1. So this is the first order for CO2. So the overall order is what? Come on. 2 plus 1 is 3. So the overall order is, oh wait. Did I do something wrong? Did I do something wrong? 2 to the y equals 1. Oh, so y was what? 0, not 1. Silly me. I need to change my glasses. 0, because 2 raised to the 0 power is 1. If I raise 2 to the first power, it'd be 2. Some of y'all were in there. I know Deshaw, if he's listening to this, he caught that. So 2 to the first power is 0. So the overall is 2 plus 0, right, is going to equal the second order. So it's second order overall. Sorry about that, guys. Long day. All right. So now to find the rate. The rate is going to be equal to K times NO2. That's the only thing that's going to mess with it. So K equals the rate divided by NO2. So that's going to be, and I'm just going to take the first one like I normally do, the rate 0.0021 from experiment 1 divided by NO2, which is 0.10. Big difference. And so that's 0.21 times 10, just molar minus 1, second minus 1. Okay, so that's the K. So that's how I got K. So if I were going to do this with the rate way that I showed you just a minute ago, I call it the alternative method because it's alternative to me because I don't want to do it. And I wasn't sure. I could take any experiment and I could find the rate A to the rate B, okay, and then I could figure out what those were. So if I wanted to do like A, for example, I would put rate the rate of 2 over the rate of 1. Usually you want to put the big number over the little number, that way you don't have to deal with fractions. And then you put the concentration of A in each of those, okay? And then, you know, figure that out, and then that'll give it to you. So in experiment 1, let's see, I'm going to do 2 and 1. Experiment 2 and experiment 1. I'm doing that because the bigger number is in experiment 2, and so I want a whole number because it's just easier to work with, okay? So to do this, I'm going to have the rate of 2 over the rate of 1 is going to be equal to the concentration of NO2 in the first one, in number 2, the second run, divided by the NO2 in the first run, and I'm going to have to raise that to the x power, remember? Okay, and so the rates, let's see, so 0.0082 divided by 0.008, or 21, sorry, is going to give me 3.9, okay, 3.9, right? Looks like 4 to me. Oh, yeah, 3.9. Okay, so 3.9 is the rates. So then the 3.9 is equal to the concentration of NO2 in experiment number 2, which is 0.20, divided by the concentration of NO2 in experiment 1. And then all of that is raised to x. And then to get rid of x, what I've got to do is I've got to have, let's see, I've got 2 divided by 0.2 divided by 0.1 is 2, okay? So that becomes 3.9 equals 2 to the x, right? So then I take the log. So I'm going to divide 3.9 by 2, right, to get rid of that. So I'm going to have to take the log of 3.9 divided by 2, and that'll get the exponent part off the x, make it into just a regular x. Okay, so it's the log of both of them, and so that's going to end up x. Well, and so you take the log of that, divide them, and then that is going to give you x, which is 2. And I already knew that because I already did it the eyeball way. And if you can put the CO in there, but you know it's going to be a 0, and so it'll tell you really quick in your calculations that that's going to be 0, and so you won't have to worry about that one. But you do the same exact thing if you're looking for the CO, if you don't look at it and tell that nothing happened in the reaction. So again, I was using the 14.2 information to do this, and you get the same number, super close. You got to use whole numbers. So I mean, if it was 1.99, you're going to have to round it to an integer. So 2. So it's easier with the first method because it's always going to be a whole number. All right. So that's how you do it with the alternative method. So I did it both ways for you so you could see that they do actually come out the same. All right, and so this is the one I was doing just then. It's this 14.2. So then you're going to have a for practice. And these are the ones that you need to make sure you can do. And you should be able to go by the ones I did as examples and be able to figure those out. So that's the end of part 2.